Hello everyone. Today we're going to go over section 5.5, dependent events and conditional probability. First of all, before we can talk about conditional probability, we must describe what dependent events are. These are events whose outcomes are affected by each other. So for example, you can have two cards drawing from the same deck of cards without replacement. Then the outcome of the second event depends on what you drew first. Case in point would be, let's say you are drawing a card out of a deck of cards and you're looking for aces. So you can see that there are 4 aces out of 52 cards in a deck of cards. Now, if you drew an ace on your first card, there are only 3 aces remaining out of 51 cards. But if you didn't draw an ace on the first card, then you still have 4 aces left in the deck out of the 51 cards still. So that would be a classic example of dependent events. In order to do this, then you must be able to identify whether two events are dependent or not. So we have some examples here. Example 1a, the experiment consists of choosing 2 bills without replacement from a purse containing 4 $5 bills, 5 $10 bills, and 3 $20 bills. The first event is that the first bill is a 5, and the second event is that the second bill is also a 5. So because the money is taken out of the purse without replacement, these will be dependent events. So the key phrase here is without replacement. Second part, it says the experiment is rolling a die and then rolling the same die again. Now, obviously, the die roll will not affect one another, so these will be independent events. So usually, in the context of independent and dependent events and probability, we have to have a notation. So dependent events are denoted usually with some kind of conditional probability statement. So we can see here we have the probability of B given A. So this is once again read as probability of B given A. In other words, the probability that B will occur given that the event A has already occurred. So you can say right as occurred here. Okay, let's look at some quick example of dependent events. Usually, you will use a tree diagram to solve these problems. So let's see. A computer manufacturer knows that out of 100 chips, 3 will be defective. Joyce draw 2 chips at random from a box. Determine the probability that both chips will be defective. So we are looking at the following. The first chip that Joyce draws could be defective, so defective chip 1, or it could be not defective. So not defective chip 1, we can use the complement symbol here. And then we move on to the second layer. The second chip could be defective or not defective as well. So that would be defective chip 2, defective chip 2's complement, so not defective chip. And then likewise on the right-hand side as well. So let's consider the probability of each part. The first chip, there are still 100 chips, and 3 of them can be defective. So this will be 3 out of 100. And the 97 chips that are not defective will be on the right here in the complement. Okay, so when Joyce draws the second chip, you will only have 2 chips left that are defective if you're moving down to the left-hand side here. So that's 2 defective chips out of 99 chips left over. or if the first chip that you Joyce drew was defective, there are still 97 chips that work. Likewise, we have if the first chip was not defective, then you still have 3 defective chips left out of the 99 that you can draw on the second drawing of chips, and only 96 working chips left if you want to draw not defective chip and a not defective chip again. So the formula that we'll use to calculate this kind of probability is as follows. We're looking at the probability of A and B. Recall that this is the AND or intersection symbol, is equal to the probability of A multiplied by the probability of B given A. So in this case, the probability that we're looking at is that the first chip is defective and the second chip is defective. So for that, we need to multiply together the probability that the first chip is defective and that the second chip is defective, given that the first one was defective. And so in this case, we're looking at the probability 3 out of 100 and then 2 out of 99. So 3 over 100 multiplied by 2 over 99. And then we can multiply that out. That will be 6 over 9900, which could be reduced to 1 over 1650. And if you want to write as a percentage, that will be 0.06%, approximately, after you round it. Okay, so we can look at a similar example. 2 cards are drawn from a deck of shuffled cards, 52 cards. What's the probability that the first card drawn is heart and the second card is also a heart if the experiment is carried out without a replacement? So initially, once again, we want to draw a tree diagram for this one as well. So the first card could be a heart or not a heart. So we have H1 for heart 1, and then H1 and not for the first card not being a heart. Now, if you think about it, the hearts will be 1/4 of the deck, and the not hearts will be the other 3/4. So those are the associated probability for the events. The second piece will be drawing a second heart. And of course, that depends on what the first card that you drew was. So this will be heart 2, not heart 2, heart 2, and not heart 2. Okay, so if you drew one of the 13 hearts in the deck, you will only have 12 hearts left over out of the 51 remaining cards. And because you took 1 heart out of the deck, you still have all the not hearts left over, so that would be 39 out of 51 for the card to be not a heart in the second drawing. On the other hand, if you drew a not heart at the beginning, you still have 13 hearts left out of the 51 cards that are left over, and the number of not hearts will decrease by 1. Okay, so you can see that the sum total here will still add up to 51, the number of cards in the deck left over after you take 1 out, and likewise 13 plus 38 is also 51. It might be beneficial to not reduce the fraction right away and leave this as 13 out of 52 at the beginning, so you can have a better understanding of where the numbers are coming from. Okay, so we are looking for both the cards to be hearts, so that would be heart 1 and then heart 2. So let's calculate the probability here to the right. So it says, once again, we want probability of heart 1 and heart 2. That is equal to the probability of heart 1 multiplied by the probability of heart 2 given heart 1. So that would be, in this case, 1/4 multiplied by 12 out of 51. And in this case, you can simplify the fraction a little bit. Goes 4 and 12. You can divide. Have 3 and 3 and 51. You're left with 17. So the answer that you can have is just 1 out of 17. And then you can use a calculator, and this works out to be just under 6%. Okay, so this tree diagram is going to be very useful for solving the kind of questions we're looking at today. Now, so far, the first two examples that you have seen are about a single branch. So in this case, you're looking for hearts 1 and 2. In the previous example, you're looking for 2 defective chips back to back. Now, it's entirely possible for me to ask you about, oh, first chip is defective, but the second one isn't, or any of the 4 branches that you have here. What about other question types? Well, let's look at example 4 together. So I'm going to change this one slightly. This question here. Don't want to do the same question 3 times. Okay, so we just want the second card to be a vowel. And then we'll read the question and see what this is talking about. Okay, so it says each of the 11 letters from the word mathematics is placed on a separate card. A card is drawn and not replaced, and then you draw a second card. What's the probability that the second card is a vowel? All right, so let's look at the probability of each step. Again, you want to draw a tree diagram here. So the first card that you draw can either be a vowel, so V1, or not a vowel, V1 complement. And then after that, you still have a second card to go through, so let's do it this way. So it could be vowel, not a vowel. So that would be V2, and then its complement in each case. Okay, so how many vowels are there in mathematics? Well, there is an A, an E, another A, and then an I. So that's 4 vowels out of 11 letters. So the probability of drawing a vowel in the first try is 4 out of 11. That means there is a 7 out of 11 probability of not drawing a vowel. From there, you will have only 10 cards left, 3 of which is vowels. If you drew a vowel the first time, you will still have 7 not vowels. And over on the right-hand side, if you drew a consonant on the first drawing, you will have still 4 vowels left, but you will only have 6 consonants left. Okay, so you'll notice this time around, it doesn't ask for just one branch. It asks for all branches where the second card is a vowel. So it's actually 2 different things that it's looking for. This branch is a possibility. So yeah, this branch is a possibility, and this branch is a possibility. We're not looking to see what the first card was. We just care that the second one is a vowel. So how does that look? Well, we have to consider then both cases. So the probability of the second card being a vowel, so V2, is equal to the combined probability of both cases. So it could be that you drew vowels back to back, or the first card you drew was not a vowel, but the second one that you draw is. Right, so now we can use the formula from page 1 to see how to calculate the probability. We have probability V1 multiplied by the probability of V2 given V1 plus the probability of the complement of V1 multiplied by the probability of V2 given, once again, the complement of V1. So we have the numbers over to the left. The probability of drawing the vowel the first time is 4 out of 11. Drawing a vowel again will be just 3 out of 10. Now the probability of not drawing a vowel the first time is 7 out of 11. And then the probability of drawing a vowel the second time will be 4 out of 10. So it makes sense that the first term here is less likely because there's fewer vowels and consonants. So that would be 4 times 3 is 12 out of 110 plus 7 times 4 is 28 out of 110. So that will be 40 out of 110. So really 4 out of 11. And once again, if you use the calculator to figure out the percentages, you will get 36.36 repeated. Okay. So that's how you would handle the questions where it asks you for multiple cases. Okay, next up, very similar question here. Hillary is the coach of a junior ultimate team. Based on the team's record, it has a 60% chance of winning on calm days and 70% chance of winning on windy days. Tomorrow there's a 40% chance of high winds. There's no tie, so you either win or lose. What's the probability that Hillary's team will just win tomorrow? So it doesn't winning regardless of the weather. Okay. So here, once again, you want to draw a tree diagram. And you can see that the winning probabilities are based on weather. And there's only 2 weathers of interest, either it's calm day or not a calm day. And then the team can either win or not win. Okay, so you can see that every single question we've done so far is a good idea to draw the Venn diagram. So we have win, not win, win, not win. So if there's a 40% chance of high winds, that means there's a 40% chance of it not being calm. And then there is a 60% chance that it is calm the next day. All right. So on calm days, the team has a 60% chance of winning. So this is 60%. If it doesn't win, it loses. So 40% here. And then 70% chance, so a better chance of winning on windy days, or just not calm days in general, versus 30% chance of not winning. So, similar to the last example then, the probability of a win is equal to the probability of winning and it being calm, plus the probability of winning when it is not calm. So here, in this case, you're looking at the probability of winning multiplied by the probability of that would be winning when it's calm multiplied by the probability of it being calm tomorrow, plus the probability of winning when it's not calm weather multiplied by the probability of the weather not being calm tomorrow. And you already have all these numbers to the left based on the tree diagram. So that's if you set this tree diagram upright, then you're going to be okay. So let's see, that will be 0.6 multiplied by 0.6 plus 0.7 multiplied by 0.4. So 0.6 times 0.6 is 0.36. And then the second product will be 0.28. And so if you add together, that's 0.64, which means Hillary's team has a 64% chance of winning tomorrow, regardless of the weather. Okay, so that's it for today. The next couple of examples on page 3 are very similar. I will leave you with the answers to those and let you work on, let you try to work out those two. And actually, the answer for example 6 and 7 are the same. And that is to say, the answer is 5 out of 12 in both cases. Or I believe I wrote as 41.6% repeated. Alright, so that's it for today. Thank you for listening.